Hello everyone. In this video, I'm going to show you a couple of very useful functions that you can use to derive the equations of motion for robot or any other system. If you derive them using MATLAB Symbolic, and then since these equations cannot be solved analytically, they are highly nonlinear. If you want to solve them numerically, now you have to convert these symbolic equations into what? Into equations that can be used by ODE45, ODE15, or any numerical solver. You know, those solvers typically handle first order ODEs, so now you have to convert the second order ODEs that you have, these equations of motion, into a bunch of first order. You need to use the dummy variables and go to the state space model basically. If you use these functions, it makes life a lot easier. It makes it all automated. Because if you don't, when you get those symbolic equations, now you have to manually assign some variables and then rewrite everything in terms of those dummy variables to write your ODE function, right? To write that function that you always pass to ODE45 or anything, so you can use it. So can everything be basically automated so you don't need to do any manual work, all done in MATLAB automatically? Yes. To demonstrate that for you here, I'm going to show you the 2DOF planar arm robot, where the length of the members, the mass of the members, G, and the torque applied to both motors for member 1 and member 2 are selected as these numbers for numerical solutions. But first, look, when I want to derive the equations of motion using Lagrangian method, I do it all automatically using the symbolic MATLAB. So here I choose Q1 and Q2 as functions of time, so I can take derivatives from them, and G and T1 and T2. And if you remember, in Lagrangian, we need kinetic energy, we need potential energy, and subtract to get Lagrangian. So kinetic energy, you know, for a rigid body is 1/2 mv of centroid squared plus 1/2 omega squared times I about the centroid. But I about the centroid should be basically transformed into the base coordinate frame, right? So here you see this one is m times v of the centroid transpose times v of the centroid. So that's 1/2 mv squared, and this 1/2 is multiplied by the whole thing. And then 1/2 I omega squared. This is the omega squared, as you can see. And this term here, R1 I of about G1 times R transpose, this is to transform your I from the body attached frame to the base frame, where R1 and R2 are the rotation matrices for the two members, okay? So this one is for member 1, the bottom one is for member 2, and the whole thing is kinetic energy. And potential energy is just mg times y of the centroid, and these are y of the centroids. So if I go back, R of centroid 1 is L1 cosine 1 over 2, right? And L1 sine Q1 over 2, if we assume the centroid of mass member 1 is in the center, and Z is 0 because it's a planar robot. The second member, L1 cosine Q1 and L1 sine Q1, this is the endpoint of member 1, and then you add to it L2 over 2 cosine of Q1 plus 2 and L2 over 2 sine of Q1 plus Q2. So this is R of centroid 2. So now if I want V of G1 and G2, I simply take a time derivative from RG1 and RG2 with respect to time, so I can plug them right into this formula, okay? Then I's for the body attached frame, you know, if we model them as a slender bar, we have I about Z, which is mls squared over 12. Also m about y axis is mls squared over 12. And x-axis is along the member. Since they are slender bars, I about x is 0. And there is no product term, so these are the inertia matrices about the body attached frame for member 1 and 2. Rotation matrices are rotation z's, as you know. So the first one is rotation z angle q1, the second one is rotation z angle q1 plus q2. And omegas here, which I showed with W instead, are 0, 0, Q1 dots, right? And the second one is Q1 dot plus Q2 dot, that is omega 2. So now when I plug in everything here, I can get my kinetic energy and potential energy. Again, is mgy for each member is added together. And here you see this is y of the first centroid, and then the y of the second centroid, which is this one, is plugged in right here. Okay, so that is my potential energy. I subtract to get Lagrangian, and then here I have my Euler-Lagrange equations, which, if you remember, that's the time. First, you take time derivative of L with respect to Q1 dot and Q2 dot, right? Which are these inner parentheses term, these ones. This is partial derivative of L with respect to Q1 dot and Q2 dot. You take a time derivative of them, which you can see here, minus the partial of the L's with respect to Q1 and Q2. And here, the only non-conservative terms we have, because we don't have friction here in this model that I'm using, right? You can add frictions on the right-hand side. The only non-conservative things are the torque 1 and torque 2 on the other side. So these are my governing equations, as you can see, this one and this one. I simplify them, and then I convert all of those fractions, big fractions that you get from symbolic, I convert them into numerical numbers using VPA and 3 numbers. So I get equation 1 and equation 2, right? So let me first show you this part so you see what I'm talking about. So if I run this for you, okay, you should get your equation 1 and equation 2. There we go. That's equation 1. This is equation 2. Now equation 1 is, of course, a large equation. And now, how would you, now that you have these two governing equations, how would you go about solving them? Because if you remember from one of my previous videos, these equations are quite a bit large, non-linear, and the only way to solve them is numerical. Okay, this is that previous video that I mentioned to you, if you remember, on my robotics playlist, equations of motion for n-link robot in jointed space using Lagrangian. So these are those two equations that you see, okay? The equations will be of this form. And now, if you want to solve them, you have to what? You have to, because they are both second order ODEs and nonlinear, you have to choose 4 dummy variables. And if you remember, we picked our dummy variables like this, or any other format, as long as we can convert them to first order ODEs. So Q1, Q1 dot, Q2, and Q2 dot are those first dummy variables that we chose. And then basically we rewrote those governing equations into something like this. A Q double dot equals the right hand side. Then we solve for the Q double dot, which is going to be A inverse of A times right hand side. And then the first derivative, the first element of that solution is Q1 double dot. The second part of that solution is what? Q2 double dot, which are going to be the time derivative of Z2 and Z4, remember? And if you looked at this demo that I showed you, if we wanted to do a forward dynamics problem, we had to what? We had to use ODE45. We had to convert everything into those first order ODEs that I mentioned. You can see them here, I assume, right? You can look here. There we go. You see here? So you have to, this part, going from these equations that you derive symbolically to these ones that ODE45 is using, we did that manually. We did this part manually, and we wrote that ODE function for these 4 equations manually. Now my thing is, could you do it automatically? And the answer is yes. Let's see how. So MATLAB has 2 very valuable functions that can help you with that. What are they? Let's take a look now. So the first function that you have is this guy. Is called reduceDifferentialOrder. This one is the one that converts your higher order ODEs, second order in this case, to first order. So you have 2 second orders. This one will automatically convert them into 4 first orders. So it selects those dummy variables by itself, and it will give you those first 4 first orders. How? So this is the way you use this function. You combine your 2 equations that you got, equation 1 and equation 2, into these variable equations, And then you say these equations with respect to the variables q1 and q2, which are the variables in these equations, reduce differential order. And it returns to me the equations and the variables. What are the variables? These variables are those dummy variables that you should choose. And these equations are those 4 first order ODEs now. Okay, so let me show you that here. Right? So this is what we do. Look here. We do that, and look. These are the 4 dummy variables. Look, q1, q2, dq1t, and dq2t, which are q1 dot and q2 dot. You see? So it chose them, and the order that it did is q1, q2, dq1, and dq2. This is how it is chosen, okay? So when you want to plot them later, you have to pay attention. It's the first and the second column of Q that you should plot, not the first column and the third column, because the order here is different than what I typically choose. And the 4 first order ODEs, if you look at them here, the first one is very long, but look, this is the first one. As you move on to the right side, you can see here the second one is starting. And as you move further, you should see the third one and the fourth one. Okay, yeah? So here, this amazing function will give you all of the first 4 first order ODEs. Okay, seems like this 4 first order ODEs is a tongue twister for me. I cannot easily say that. So now what? Now it converted them into first order, but still not exactly solving for q double dots. Okay, remember the goal is to solve for q double dots. So this is still not done completely for it, just rewrote them into first order, but not solve for q double dots. So if you want to solve for q double dots, you need to use a couple of other things here. What is that? The next one is you pass those equations and those variables to this new function called massMatrixForm. So now it is going to put it in this format for you. Now it is going to put it in this format. But instead of A that I called, it calls it M, and instead of right-hand side, it calls it F. Okay, so here, this means what? It means M times Q double dots equals what? Equals F. So it converts the equation into this format, and now by multiplying inverse of M by F, or M backslash F, it is what? It is solving for it. So now it says Q double dots equals inverse of M times what? Times F. So you see it is solving for Q double dots. Now these F's are those final first order ODEs that I talked about. And now you got these equations. Can I now use them in ODE 45? Not yet. They are symbolic equations. So now you have to what? You have to convert these symbolic ODEs into function handles usable by ODE 45. You have to convert them into function handles, because remember, ODE 45 uses a function handle, not symbolics. So what would you do now? This is your next function, ODE function. This ODE function will take those symbolic ones with those variables and convert them into this ODE fun, which are those 4 function handles. Here I use 4 initial conditions of 0, feel free to change it, and I simulate my system for 1 second. I passed it to ODE 45 and I get T and Z, and now this is what? Ready to go. Finally, once the solution are in, I plot the first column and the second column of Z, which are Q1 and Q2. And remember, how did I know they are the first and the second? Because I looked at these variables. I knew which ones they are selected as Q1 and Q2, And now if I run the whole thing all together, you should be getting your numerical solution. Look, there we go. Okay, so this is Q1 and that is Q2 here. And Q2, you see it's oscillating. Q1 is just going straight up. And that is probably the reason that torque 1 is high, torque 2 is low. So if you bump up torque 2, probably you should be able to get more of an upward trend for member 2 than just pure oscillations. Okay, there we go. You see here? Now member 1 shows some crazy behavior too. It just does a sudden transition. But you see now member 2 is kind of going up. Member 1 is showing this sudden transition here, right? And you know that now my motors are both having enough juice to increase the angles, but here again I have some sudden change in behavior, which is kind of expected. So you see here I have not used anything manual. Everything is generated symbolically first, then reduced to lower order, converted into finding for Q double dots, creating function handles, and now ODE45. So you learned 3 new functions today: reduced differential order, massMatrixForm, and ODE function. And these are extremely powerful. Okay, so hopefully the video was useful to you, and I'll see you in the next lecture. Thank you.